In doing so, we would exceed the octet on that carbon. So what do? Shuttle those pi electrons onto that carbon. The result of that would be a resonance structure that looks something along these lines, minus all the hydrogens because I don't feel like drawing them. We now have a negative charge on the ring. Okay? This is why the EAS reactions, in my opinion, are the easiest reaction to deal with, because it's all resonance. All you have to do is to be able to manipulate your resonance structures and you're done. Everything else just falls out. So it's a nice reaction in that case. Let's take a look at what happens in the bottom case. We have a positive on that oxygen, or X. Okay? So that means to stabilize it, the electrons could come out to stabilize it. In so doing, what happens to this carbon?
It becomes positive.
It now has lost electrons and it becomes positively charged. Note we end up with the same kind of core structure. We have a double bond to atom X, but the charge on the ring is different. In the red case, the charge on the ring is negative, which would mean it would be likely to act as a nucleophile. In the blue case, it's positive. Remember, the whole point of the ring is to act as a nucleophile in an EAS reaction. If it's positive, can it act as a nucleophile?
No.
No. What does that mean? The red case is activated. It's a stronger nucleophile. So we can reference that as an activator. Atom X activates the reaction. What happened with atom X in the blue case? It deactivates the reaction. We now don't have electrons to run the reaction. If we propagate these resonance structures out with all the arrows, we will get something that looks like this. Okay? The speed of those drawings should happen insanely fast, admittedly not as fast as me just hitting the next button, okay? But it should happen very, very quickly, and ideally it happens in your head. And you would see where those charges fell in each of those cases. Okay? If we summarize it, we'll call the top case our red case. We end up seeing negative charge build at these positions. Undo that. We'll just do a dotted line all the way through, a solid line and a dotted line out to our X. Okay? Which means those positions on the ring are now super activated for an EAS reaction. Okay? So not only did atom X activate the ring to react, but it made those positions more active. Well, based off our discussion on Wednesday, what are those positions called? Para and ortho. Okay. You will sometimes hear atom X being referenced as an ortho-para director. I am guilty of that. I'm trying desperately to get to para-ortho, not ortho-para. Why would I want to say para-ortho and not ortho-para?
Because ortho can modify para, and not vice versa. Do you know Latin or Greek?
No.
Tell us a lesson.
I want to know about its reactivity. Where's the first substitution going to happen? Para. If I say ortho-para directing, where's my first substitution?
Para.
It's still para. Okay? But when we call it ortho-para, what's your reflex? To put it at the ortho. Okay? Your first substitution is going to happen at the para position. Why should it happen at the para over the ortho? If we go back to our starting structure at the very beginning, what we're talking about is how the electrons within that structure leave. So we'll call it a purple arrow leaving the structure. That would then get us an ortho substitution, or we'll call it a green arrow, green works, right? Getting us a para substitution. Why would green be better than purple?
Not near a functional group.
Say it again?
It's not near a functional group.
What do you mean by not near a functional group? Yes.
X is going to be more reactive than hydrogen?
Well, except more reactive.
Steric.
It's a steric argument. X has more electrons than hydrogen, which means it's bigger. Which means for the electrons to leave the structure, they would have to pass by other electrons. There's a steric repulsion. That steric repulsion limits the activity at the ortho position. That's why the para tends to react first. Notice I did say tends. It's not a huge differential, but there is a significant differential where the para reacts first. So if we were to run a single substitution, I think it comes in at 60-40. Okay? And it depends on what atom X is. For instance, if I made atom X something like this, what would I expect now? Almost exclusively para. So it is very clearly a steric effect that's happening here. The larger atom X is, the bulkier it is, the less ortho I see, the more para I see. Okay? So para is weighted heavier. It's an steric effect, not an electronic effect. Yes?
That is assuming that X is the only thing attached, right?
And at this stage, all we're doing is assuming that there's only one atom X on there, and we've got 5 hydrogens. Yes, it's going to get more complicated if there's more things there. Okay? But what we will need to consider is kind of our subsequent stages, and we'll deal with that in a second. Okay? When we move to the blue drawing, what was our result? We're still building charges at the exact same positions as we are in the para-ortho, but those charges are positive. This is why that ring is deactivated, because in an EAS reaction, it must be a nucleophile. If I have positive charge, I don't have a nucleophile. So atom X now deactivates that structure. Where does it end up reacting? Let's say we react it with a strong enough electrophile that it is now forced to react. Where should it react? It's now going to react to the meta positions. It won't react at the ortho and para because it literally doesn't have the electrons to do the reaction. So it's going to react at the only space where there are electrons, which is the meta position. Kind of make sense? So what you can go through and do is now take that to the bank and memorize what's in bold. Evaluate atom X. Does it have more electrons than hydrogen? It's an activator, para-ortho directing. Okay? So you don't have to draw out all the resonance and all the mechanisms. You can just jump to those pieces. Make sense? Okay. Same deal. Atom X has less electrons than hydrogen. That one's a little bit trickier to see. Okay? But if it has less electrons than hydrogen, then it deactivates and it's a meta director. Okay? There are a variety of atom X's that have less electrons than hydrogen. I'll just draw the 2 most common ones that you'll see. Atom X is this nitrogen from a nitro. So there's our benzene ring down here. That nitrogen would have what charge?
Positive.
It would have a positive charge. And we would know that why?
Got 4 bonds.
We could do it based off of what we memorized from Unit 1 in Semester 1 of OChem. A nitrogen with 4 bonds is a positive charge. Or
It's a nitro group. Nitro's going to be,
you could memorize that a nitro group has a positive nitrogen. Or
there's a positive, you have to maintain charge. Charge is conserved.
Formal charge.
we don't necessarily know that there's a positive.
Could you calculate formal charge?
You could calculate the formal charge. How do we calculate formal charge?
Valence number minus
Valence electrons, nitrogen has
5.
5 minus.
Bonds.
How many bonds are there?
Half.
Just shush with your half thing. We'll address that in a second. Minus bonds
Bonds.
minus
Lone pair electron.
lone pair electrons. Does that nitrogen have any lone pair electrons?
No.
Did the oxygens?
Yes.
Yes. That can become tricky. Why do we know the nitrogen doesn't have any lone pair electrons?
They would exceed that.
It has its full octet. Why do we know the oxygens do have lone pair electrons?
Besides those, they don't.
Their octets weren't shown. There are implied lone pairs on those, right? Okay, for those of you thinking, oh, that's basic stuff, I don't need to worry about that, you get test questions at that level on the final. Okay, so you should be familiar with that. Those should be gimme points. Right? Minus non-bonds, 0. 5 minus 4 minus 0 is 1. Or better said, +1. That's why we know the nitrogen's a positive. For those of you that want to go old school based off of how Gen Chem said to calculate formal charge doing this weird half thing, if you don't know what I'm talking about, ignore it. Okay, if you do know what I'm talking about with the weird half thing, the only reason that exists is because Gen Chem is concerned about units, and the calculation we just ran doesn't have proper units. Does it have the proper flow of logical thought? Yes. Focus on the proper flow of logical thought, not on the minutia of proper units. It's okay. Right. Next one that we can look at. Whoops. Might help if I don't exceed octets. Atom X activating or deactivating? Hard question, so let's change the question. What is atom X? Carbon. Does that carbon have more or less electrons than a hydrogen?
More.
When in doubt and you're curious about the reactivity, what should you do? Draw a resonance structure, and when I draw that resonance structure, what do I see happen to my carbon? Loses octet, and more importantly, positively charged. Does a positive carbon have less electrons than a hydrogen? Yes. A hydrogen atom has 1 electron. To have less electrons than a hydrogen, you must have some form of positive charge. Okay? A partial positive charge counts. They're not always formal. Make sense? Okay. So those are the two most common. The nitro, which is again kind of a gimme. They make that one a little bit more difficult because they don't show the Lewis structure. They would write it out as, of course, all the stuff underneath. NO2. Notice there's no charge associated with that. Why? When we drew out the Lewis structure, the nitrogen was positive and the oxygen was negative. Net result? 0 charge. Okay, so they'll hide the charge in the formula. I don't agree with it, okay, because I think you should be evaluating structure. But by that same token, you should be evaluating structure. If you see a formula, you should turn it into one. Okay? Or you do as David suggests, you memorize that a nitro is withdrawn. Either's fine. Make sense? Okay. Yeah. So let's look at some of the kind of more challenging ones. Remember we said alkylation required an active nucleophile. We need an active nucleophile because the electrophile here is so incredibly unstable that it forms and reforms our stable halide so fast that I need an active nucleophile to step in and react and prevent that reverse. Does that make sense? So our electrophile is incredibly unstable there. Right? I need an active nucleophile to react with it immediately. In the case of the acylation, that electrophile is much more stabilized, which means it exists for a longer period of time. Because it exists for a longer period of time, we increase the chances that our nucleophile can come in and interact with it. Right? So our acylation forms a more stable electrophile, which gives us enough time to react with the nucleophile regardless of its level of activity. Okay? I do want to note massive typos in how those are presented in the slides, because if you look at the slides, it actually says the inverse. It says the alkylation is not or is stable and the acylation is not stable. That's actually wrong. Okay, it's a time issue with those. Yes?
So you couldn't do an unstable electrophile with like the
A deactivated ring. That's not going to work well.
Okay.
Yeah. And the reason why is that your unstable electrophile doesn't form very high concentrations. Your deactivated ring is now also not very high concentrations of the nucleophile. So the odds of them ever actually encountering each other where they are active is next to nothing. Right? So you need them to kind of balance that out. Okay? I just like to reference it, and I haven't referenced it yet. Why is this cation incredibly stable? Nope. Okay, and for those at home, why are we referencing that as incredibly stable? Is that a good Lewis structure? No, it's a bad Lewis structure because
There's a charge.
charge is a requirement. Octet. The carbon is missing its octet. How can we make that more stable?
Can you make a third bond in the oxygen?
Oxygen lone pairs can donate down. I don't know how I missed this joke earlier in this unit, but I did. This happens to be one of my favorite cations because it's a little bit silly. You're like, what?
There's a name, isn't there?
There's a name.
There's a name.
It's a psyllium. There we go. Yeah. I got it after the first one. It's the Acylation ion. It is commonly referenced, again, because they'll hide it behind the triple bond, making people think the oxygen's reactive. Okay? Remember, if you're thinking about reactivity, if the oxygen's going to be positive and act as an electrophile, an electrophile, it needs to accept more electrons. It has 8. It can't accept more electrons. Look to that first resonance structure. That's showing the reactivity. Okay? So, alkylation requires the active nucleophile. Acylation, it doesn't really matter the ring. It's going to fire away. Okay? There are some other complications that come with this. The particularly activated ring with a nitrogen connected to it. Okay? This species is known as aniline. Okay? Which, was that your unknown? No. Did you write the EAS lab report?
Put him on the spot.
Just being honest.
Well, just crap. Aniline, you may or may not be required to actually know that as a name for that, as a common name. Okay, it could pop up. In the case of Friedel-Crafts, anilines aren't very good. Okay, and the reason being is that nitrogen lone pair is exceptionally reactive. Okay, it can react with acids, including the Lewis acid catalyst. When it reacts with the Lewis acid catalyst, what happened to atom X? Became positive. Where was atom X to begin with? Donator. An activator with
You almost got it.
with electrons. As soon as we do the Lewis acid catalyst, it now becomes a deactivator. Okay? I would like to say that's consistently shown, but those of you in lab can probably also notice that it didn't actually deactivate the reaction. Okay? In that case, it was a Bronsted-Lowry acid catalyst, not the Lewis acid catalyst. The Lewis acid catalyst seems to be more clear cut and dry, that if you see a Lewis acid catalyst with your nitrogen, you're not running the reaction. Kill it. Okay, be it alkylation or acylation. Okay? The next one that's fun. Okay, so we're running the alkylation. We know it's an alkylation, not an acylation, because why? Acylations require the carbonyl. There's no carbonyl. Okay, so we're doing a strict alkylation. If we were to run this reaction, where would we expect the alkylation to occur? Okay, so when you see this, what you should be seeing is that this means CH3 positive. You now have to decide where you should place that CH3 positive on that ring. David,
Para position.
why would you go para?
The oxygen and the ester, or the ether, is going to be donating. So it's going to donate down, so you've activated your ring. 3 spots, one is a bunch of electrons next to it, and like the A is sticking out. You'll get 2 products, but you're more likely to get the para addition than the other addition.
Oxygen, as atom X directly connected to the ring, has more electrons than hydrogen. It's a donator, which makes it an activated ring. So it should react with our Friedel-Crafts alkylation, okay? And it directs para and ortho. So again, if you just memorize that X has more electrons than hydrogen, yes, para-ortho. Ta-da! And because we memorize it as para-ortho, we put it in the proper first place to put it. Make sense? Okay. Let's take a look at that product. How many atom X's, if you will, are on that product? Someone mouthed it. 2. We've got the oxygen and the carbon. The oxygen is what kind of atom X?
Neutral.
It's an activator because it has more electrons than a hydrogen. It's literally the same oxygen we started with. Nothing about it has changed. It's still an activator. What happened to carbon? I thought I said oxygen. Did I say carbon?
I thought you said carbon.
I heard oxygen.
Maybe I-
Okay, you lose. Next question, carbon. What about carbon? It is neutral, so is the oxygen.
That's activated.
Doesn't count as an answer. More or less electrons than a hydrogen.
I think it does this. Isn't it the same? 'Cause it's
Hydrogen has how many valence electrons? 1. Is that carbon positively charged for any reason? No. Which means how many valence electrons does it have? 4. Which is greater, 4 or 1? 4, which means the carbon is activating. Is it as strong an activator as the oxygen? No. So we can nuance differences in the levels of activity. The oxygen is absolutely a stronger activator, but the carbon is also activating. What does that mean about that ring?
you've got 4 activation sites now.
It is more reactive than I started, which means
Cascade effect.
now I have to run the alkylation again. My product is actually more stable than my starting material. The reaction goes again. This is just like the amines that we talked about way back in Unit 1. And I think they even showed up in Unit 2 again. Unit 3. Okay, make sense? So now the question is, where should I place that new methyl? Because all 4 sites should be activated, right? The oxygen directs para-ortho. The para is blocked because there's a carbon there, not a hydrogen anymore. The methyl, which I'll go ahead and show in blue now, is going to direct para-ortho. The para is blocked by the oxygen, but the orthos are not. All 4 sites are now potentially reactive. Where should the next alkylation happen? Para to the oxygen is a carbon. You can't substitute that.
Ortho to the oxygen.
Ortho to the oxygen. Why should we go ortho to the oxygen and not ortho to the carbon? The oxygen's a stronger activator. Okay? So the oxygen's going to dictate where your reactivity is going to happen because it's the biggest one. The carbon is just adding more electrons into the ring, making the ring more active than we started. This means what's going to happen while I'm drawing. Go ahead, Dave, ask your question.
You'll still get a mix of products, right? Or is it
Not
just-
appreciable.
Okay.
And we'd get our CH3. Yeah?
You've now made the ring even more stable in another guiding group.
Say that again. I've made the ring now even more
Stable.
active. Okay? Because we've put another activating group on the ring, which means it's going to react again. Hence the phrase underneath are alkylations. Polysubstitutions. Okay? If you're going to run Friedel-Crafts alkylations, you typically will do multiple substitutions. And there isn't a whole lot you can do to stop that because the product of each of those is more reactive than the past one. Does that make sense? Okay. So how could we get around that? Well, we could go with the acylation. Yeah. What happens when we do the acylation? Let's see, how much do I reveal? Nope, I didn't reveal nothing. Thank you, Mike. We're drawing out all of that stuff so that I don't have to fill time with nonsense, useless words while we write the reagents. What would our products be now? What is atom X?
Oxygen.
Oxygen, activating or deactivating?
Activating.
Activating. When we look at the reagent sequence in the middle, what we should immediately be seeing is the active reactive species, CH3, the positive oxygen, yeah? I now just need to place that on the ring. Where do I place it? Well, if the oxygen is activating, I know I'm para-ortho. Which one goes first? In how we say the name, para-ortho. So we should put our first group on in the para position. And we have a product. Just like we did with the alkylation, we need to evaluate. Should this react again?
No.
Why not?
The carbon is deactivating.
The carbon that we just added to the ring is actually deactivating. The product of that first step is less active than our starting material, which means stop. Okay? Could we react again? Yeah, arguably by throwing more reagents at it. Okay? But in a standard reaction, we're stopping it right there. That's why the acylation tends to be a better reaction to run than the alkylation. Kind of, sort of? What if I only wanted a carbon chain there, though? I've got this stupid oxygen on there. I don't want the oxygen. How do I get rid of it? I could just do a reduction reaction. I get the selectivity of placing the group that I want, where I want, the amount of times that I want, and then I just follow it up with a reagent to remove the oxygen. That's why we had those reduction reactions back in chapter 19. Kind of make sense? Okay. So, next one. Do we have weird aromatic systems? Yes. Okay, we talked about atom X having more electrons than hydrogen, activator, or less electrons than hydrogen, deactivator. Dead in the middle would be hydrogen. But there's a whole bunch of other atoms we could place on there that are going to have varying scales on that, right? So let's take a look at a few before we actually look at what's on the slide itself. If I had NH2 versus OH, activators or deactivators? Both of those are activators, right? Both have, more electrons than a hydrogen. Which one is more activated?
Nitrogen.
Why the nitrogen?
So less electronegativity.
It has to do with electronegativity. Nitrogen, being less electronegative than the oxygen, is more willing to donate the electrons. Donate the electrons where? Into the ring, so that the ring can react as a nucleophile. So the nitrogen's a stronger nucleophile, or a stronger activator than the oxygen. Kind of make sense? If we switched it to carbon, it's still an activator, but it's weaker than both of those. What if we switched it to an aldehyde? Now all of a sudden it becomes a deactivator. So we have a line. It starts activators, less activating, and all of a sudden we're deactivating. Okay? Kind of like when we looked at active nucleophiles with carbons. We had Grignards that became Gilmans, that became enolates, that became diketones. Okay? There was a line that differentiated whether you could do 1,2 versus 1,4. There's a line that establishes the difference between activator versus deactivator. Establishing where that line is tricky. So everybody gives me a hard time for that being an L. That's an L. Chlorine. Why should it be a deactivator?
It's pulling electrons away from the
You're saying it's a deactivator because it is electron withdrawing because it has a high electronegativity. Yeah? Does the chlorine have more electrons than hydrogen?
Yes.
Yes. Shouldn't that mean?
But it has one valence electron.
It has 7 valence electrons, 3 lone pairs.
Its valency is 1.
Its valency is 7, and you're using terminology that I'm a little bit uncomfortable answering with, but I'm pretty sure you're going to say the valency is 7. If you drop to hydrogen, what would your valency answer be? -7?
Well, I thought how I learned valency was how many electrons you need to make it full.
I'd be careful using that definition, is all I would say. So if we look at chlorine, it has more electrons than hydrogen, but it doesn't want to share them, which means why not both? The chlorine is a deactivator, but instead of directing to the meta position, it directs para and ortho. Okay? It has the ability to do both. So where's the line between activators and deactivators? Halogens. Okay? Everything else is resonance. So to me, EAS, you memorize one thing for reactivity. Halogens are deactivators, but they're para-ortho directing. Everything else is resonance. Okay? Yes, it's weird, but that's how it works. They definitely have more electrons than hydrogen. They're definitely not willing to share those electrons. Okay? For the exact reasons that we elaborated. Ultimately, what ends up happening is that our halogens take a blend of both, which I decided to not summarize right there, so let's go ahead and handwrite that in. They direct to the para and ortho positions, and they are deactivators. Okay? They're the exception if you want to think about it as an exception to the rule. Everything is resonance except halogens that just F with the system. Make sense? Okay. After that, multiple X substituents. We've actually already kind of addressed this, but let's take a look at these. So, first thing that you should do, because you had all of Thanksgiving break to memorize, you see Br2, FeBr3, and you think
Lewis acid.
Br plus. Question is now, where do we place Br plus? It's going to do a substitution. It could do a substitution for that hydrogen or that hydrogen. Are those the same or different?
Different.
Different because?
Is there different positions? I thought that I could tell which one's which.
Okay. If we think back to NMR, those would show up as distinct hydrogens. How about this hydrogen? Different or the same?
Different.
Different. How about this hydrogen? Different. So we have 4 different locations that we could put that bromine. Which of them becomes correct?
Blue.
How do we evaluate?
You've got a meta director for the deactivated.
Okay, so let's pause a little bit. I like where you're going. Let's look at the atom X's and decide where they direct.
Yeah.
Okay. Atom X in one case is the NO2. Sorry for the crookedness. That's called cut and paste. NO2, that atom X is a deactivator, meta-directing. How about the other one?
The weak activator.
This is an activator or para-ortho directing. Which one wins? Activators always win. Okay? Why? They're the ones driving the electrons into the structure. They're going to dictate your reactivity. Okay? Would I expect this reaction to work well?
No.
No, because of the deactivated activation of the nitro. But the methyl's going to direct. So where is it going to direct to? Okay, para. So we'll go here, here, or here. right? Sorry, ortho, para and ortho to the methyl.
I would say
Okay.
3.
Which of those do we think might be the best? I heard one for a para, so saying we put the bromine here. And then I heard one for the green, challenging. Why?
Because you're usually assuming that when you do the para first, that you don't have any steric propulsion there. NO2 has a whole lot of electrons bouncing around. That's a big ball in the way.
There's probably some steric repulsion there, which would suggest that green is probably the better one. Okay, kind of makes sense? You'll still get a mix. Okay, what happens when we move to the next one? When we see that sequence of reagents, we immediately say NO2 with the positive on our nitrogen. So now the question is, where do we place it? Both of them are activators. The oxygen activates, so para-ortho. The carbon activates, so para-ortho. Which one in the top example? Activator or deactivator? Activator. Why? Because it drives the reaction. It's the thing that's activating the reaction.
Pushing electrons in.
Let's apply that same logic to the second one.
Oxygen.
The oxygen's the stronger activator. Our directing effect is dictated by the strongest activator. Since the oxygen's the strongest activator, it wins. Where does our reaction happen? Why not para? There's no hydrogen there. In an EAS, you have to have a hydrogen to do the EAS reaction. So we're going to go, I already forgot the word. Ortho, thank you. And we'll put our nitro up here. CH3, yeah. Make sense? These are the test questions that ACS likes, particularly for those of you that were concerned about synthesis. EAS is a big one for synthesis because you don't have to do a whole lot of memorization of complex reagents, but the sequence in which you do the reagents is really important. Okay? So synthesis with EAS is big. Synthesis is not a huge thing. Okay? EAS was the last thing we talked about. Okay? So you can decide if you want to spend time there or not. Largely, you've got what? 6, 7 reagents that you would just memorize what that electrophile is, and now it's just a question of sequencing. Make sense? Okay. How about the top one? So we see the reagent, and we think, in fact, the reagent works for both of these. It's the NO2 plus. Now the question is, where does it go? Ortho. Good point, because they're both methyls. So they're both activators, para-ortho directing. So yes, it's going to go ortho, but ortho to which one?
It's going to go ortho to the right one.
It's going to go, it helps if I color code, sorry.
Blue one. Or purple, whatever.
Purple. It's okay. Test isn't colored, so it's fine. It should go to the purple one. Why the purple one?
Sterics.
The sterics are going to prevent it from reacting at the ortho for the other one. We'll get our methyl, and then we'll put on our nitro at the ortho position. Good? Next one.
Is that why TNT is so explosive?
Say that again?
Is that why TNT is so explosive? Because the nitro's only go right?
Yeah, nitro has lots of high energy bonds. That's why TNT is explosive, is the nitro. Can I code it for you? Okay, so they're both activators.
The bottom, the
Ortho.
ortho to the blue one, purple.
On the bottom side.
So we're hearing an ortho to the blue.
And not in between them.
Did you do that intentionally, or did you
It looks blue from back
It's
there.
not
I
blue.
mean,
It's
It's
clearly
purple.
purple.
It's definitely
It's
purple.
Clearly
done
it's
intentionally.
You said blue, didn't you?
Well, I said blue just because you said it the first time when we went with it.
So why would we go there?
Because your para position is sterically hindered.
So if we go our ortho-para positions, right, for the purple, our ortho-para for the red, same spots, right? So it's got to be one of those three.
We're not going to use the red one because the purple one's a better activator.
You're going to see an argument where those are coming in pretty much even. If anything, I would say A is a stronger activator because there's more electrons out there. That's a long distance electron effect. I don't think it's going to be a big one. Those are both activators roughly the same.
But in the first one, you know,
Sterics is going to become the argument now. So if we look at the green circles, if we look at the blue circles,
Let's not play this game.
how many colorblind people in this class?
I don't know, but it's sounding like it's going up by the minute. The blue circles are sterically hindered. Okay? So those ones are less likely to react, which means we're going to put it ortho to the A, ortho, fudge, colors.
Para to the red egg.
You were doing it too. Ortho to the purple, para to the red.
I'm sorry.
I got it right.
Okay, you did.
This is such a struggle.
Does that make sense? So we're looking at how those things stack. Sometimes they'll stack where all positions are electronically equally valid. Sometimes they'll stack so that only certain positions are. You have to be able to look at each of those directing effects. Officially, those directing effects are coming from resonance. Whether you choose to use the resonance to help you figure it out is up to you. Does that make sense? The question at the bottom is referencing higher yields. Could we have seen nitro showing up at other positions? Yes, those would be lower yields. Between these two reactions, which one do you think would be the higher yield?
The bottom one?
I would probably actually go with the bottom one. Why?
Because the bottom one has two positions that are sterically hindered.
Top one has two positions that are sterically hindered too.
The stronger activator is para.
So-
the group is para.
Back to Mustafa's statement, the activators are roughly the same. Why is the top one going to be less likely?
They're canceling each other out.
Whoops, freaking blue. If we look at the directing effects, in the top one, they're adding or activating different positions on the ring. In the bottom one, what are they doing? They're activating the exact same positions. I would argue the bottom one's going to get a higher yield because you're getting a stacking directing effect. Make sense?
That's what I was trying to get at.
Okay. I like it. Okay, so steric, directing effects, and reversibility. Let's take a look at this. What do you think? How would you synthesize it? What changed? There's a bromine. How do we put a bromine on? It's an awful lot of white space for one reaction.
You're gonna have to stick something in that. Stick something you can pull off.
Where's our most likely reaction going to happen? Para. What do I want? Ortho. So this is not going to work in a single step. And as Dave's suggesting, we need something that we can put on and take off. We would need a reversible reaction. Just so happens there was one reversible reaction we talked about. The sulfonation reaction, H2SO4, and I think to reverse it, we still need H2SO4, but we do it in water to reverse it. Okay? It's effectively a protecting group. You're removing the hydrogen, you're putting the sulfate group on there, you're then running the bromination reaction, and then you remove the sulfate group. Okay? It's not really protecting because we are actually changing the chemistry there significantly. So that's why that textbook refers to it as a blocking group sometimes. Okay? Make sense? Okay. Let's take a quick look at this one. This one isn't necessarily a blocking group, but this gets you an idea for what you could expect. You could be asked the question, do that. Okay. You wouldn't officially be asked that. We'd give you a sequence of some reagents. What reagents do you think you'd be seeing?
BR2.
BR2, Fe, BR3. HNO3. Good. Acylation. So what's your tip off for acylation?
Carbonyl.
Okay, we could run with that. Carbonyl.
There's aluminum CL3, AlCl3.
I would run with the AlCl3 as your big tip off. Okay, that's to help pull off a chloride. And the ACS can get a bit nitpicky on those carbons, so it might be nice to actually count that out. 1, 2, 3. Make sure that you don't have a giveaway answer. Whoops. That it's something like that. That you've got your 3 carbons. Make sense? Okay. Would this work?
Maybe not in that order.
Okay. This is where synthesis comes into play with EAS. Okay. This is why they ask it. The reagents are relatively easy to know, but what is the correct order in which you run them? If we go through and put the bromine on first, it's going to go anywhere. So there's our single bromine. What happens when we put the the nitric acid and sulfuric acid? Where is that going to react? Para-ortho to the bromine, we'd get our NO2 over here. Does that match what we want? No, which means that order was wrong. Does that make sense? So what you could go through and do, you've got 4 multiple choice answers, and probably all it is a shuffling of those, is just start cranking out what those products would look like. Does that make sense? Are we good with that? Is that a yes?
Yes.
So,
Okay.
we could do the acylation first.
Okay, so that's an actual question about deciding the order, so let's look at it. Let's do the acylation first.
And then the bromination.
Where would the bromination happen? Para. And now what? And now we do the nitro. I always yell at you for writing it that way, so let me fix that. So we said 1, 2, 3.
Wait a minute, what did add there?
What do you mean?
Well, because you've got, the bromine's a bad deactivator, but either way it would be meta-directing.
Yeah, that's what I thought.
Halogens are not meta-directing, they're para-ortho-directing. They are deactivators, but they are para-ortho-directing. So I'm not objecting to the nitro
Okay,
stuff.
so then it's a deactivator, activators win.
Activators win, yeah.
So your carbonyl is a deactivator. That's right.
That carbon has what?
Positive.
Positive, which means deactivator and
Meta-directing.
meta-directing. Where does the bromine go?
And then para, okay. And then you get the stack.
Where does the bromine go?
At the meta position.
It's all right, kind of out of space. Is that what you wanted? No. So? That was a bad order.
So you could do the acylation first and then the nitro.
Okay, acylation first. Then the nitro, which means the nitro will go where? To the meta. That's looking pretty good.
But when you put the bromine on, you get the same thing, the two meta positions match up.
The two metas would overlap and you'd put the bromine there. Which means? Not right.
If you put the nitro on first, and then you follow it up with the acylation, you go meta to the nitro, and then because the carbonyl carbon is a stronger deactivating group,
I see where you're going with that, but there's definitely a better way.
Oh, I see. And then you do the acylation. And then you get the, yeah.
So you brominate, we rotate that structure. Then you do the acylation.
It goes para.
It'll go para first. Then what?
and then your ortho and meta will select for both, you get a stacking effect on that one. But you get the other one too, won't you?
You get the other one where we put the nitro over here.
Yeah.
You are correct.
It's the same.
Oh, gee.
It rotates.
Exact same structure.
Yep.
Okay, because of rotations. Make sense? Okay, so that's what they're trying to get you to kind of think through within those EAS synthesis reactions is what's the order that you put them on. They become a lot more straightforward because it's just, I'm putting this piece on, I'm putting this piece on. Where do those things direct and how do those things align? Make sense? Okay. The aromatic structure can be reduced. So just like alkynes, I can add sodium metal and ammonia. This gets named the Birch reduction, probably because they were like, you can't do that. And ta-da, yes you can. Okay. So let's go ahead and run through what we would expect to happen. What's the most reactive thing in our benzene?
The radical.
In the benzene?
The double.
I see what you're saying. Never mind. You're saying the radical on the sodium. What is that sodium going to react with radical? The pi bond. So we can take an electron out, electron out. Where's the other electron of the pi bond go? Goes to the carbon. Am I not entertaining? Sorry. I doubt the yawn actually made it into the recording. This reaction actually gets named, or not necessarily named, but you'll hear a reference to an intermediate within it. I think it's a bit dodgy to actually ask the question, but they can ask the question. This intermediate gets a special name. It is both a radical and not just an ion.
Radical.
It's an anion because we have that metal, non-metal bond. There's a lone pair of electrons effectively there. Does carbon want to be negative? Nope. What does it do?
Hydrogen.
Pulls the hydrogen from the ammonia. Okay. Places the hydrogen onto the structure. Ooh, I lied. Don't do that yet.
You can do resonance, right?
We're going to do resonance first because we want those charges as far away from each other as possible. Okay. And not even just charges as far away from each other. This now allows the radical to do resonance either direction, whereas the other situation, we end up breaking that negative charge. Now we do the acid-base reaction. Whoops, lost my radical. All right, now what does the radical do? Nah, forget about it.
The next sodium comes in and does it again.
Another sodium comes in, we form another another anion. That anion picks up another hydrogen, and we would end with our final structure in 2 more steps. So it's typically referred to as a radical anion mechanism. It's the same for the triple bond, does the same kind of thing. Okay? What makes this more interesting is if we start with something that is not all equivalent pi bonds, because every single one of those pi bonds right now is the same, right? What happens if I go through and now I change my starting pi bond to have an atom X on it?
Depends on if it's an activator or deactivator.
This is going to depend on the activating or deactivating ability of it. Okay? I'm going to end up putting a negative charge potentially at that position. Right?
So you want an activator?
Do I want a negative charge building on a position where I have an activator? What does an activator do? Donates electrons, which would mean negative to negative. That's a bad reaction. So that pi bond is not likely to react if atom X is an activator, which means one of the other pi bonds will. Okay? Which means at the end, this pi bond must still be there. Which means where's atom X in our product? Still connected to one of the pi bonds. Okay? And so the location of where those pi bonds end up is dictated based on the activating or deactivating ability of atom X and in reference to the radical anion mechanism. Okay? That mechanism is a bit of a beast to deal with, so sometimes it can be helpful to just memorize the end result. If atom XR is an electron donating group, notice, must be connected to the pi bond. If atom X is a withdrawing group, now what do I want? I don't want the pi bond. That position gets reduced. Okay? I would argue it's easier just to memorize those. You're again, at best, looking at one reaction. American Chemical Society is moving away from aromatic reactions, and we're moving more towards biological reactions because of medicine, and we're trying to keep our medical students in OChem. The only way we do that is by talking about things that are more relevant. EAS is not one of them, and aromatic rings are not one of them. Okay? So, I would argue just memorization. So, last one is kind of neat. Aromatic rings reacting oddly. Let's take a look at that top reaction. What does it look like happened?
Substitution.
It's just a substitution. Okay? The bromine was substituted for the OH. Now the interesting question, well, what kind of mechanism would that be? What substitution reactions are you aware of? SN1, SN2, and EAS. EAS, you do a substitution of something for hydrogen. Okay, we have an electrophile. Is OH an electrophile?
No.
No. So it doesn't fit EAS. If we did SN1 or SN2, we would have seen that as a reaction at the beginning of first semester or in the end of first semester. It's not. So this is not SN1, this is not SN2, and it is not EAS. So what we're seeing is an odd or bizarre behavior. Arguably, again, in my opinion, this was probably an accidental discovery. Someone threw sodium hydroxide in heat to get something to happen. Maybe they were trying to hydrolyze an ester, and there happened to be a halogen connected to a ring. We're like, well, it doesn't react in substitution reactions, I don't care. And then something happened. Okay? The question becomes is how and why did it happen? So they started to vary things and play around with it. And what they noticed was that it really only worked if the ring was deactivated. If you put activating groups on it, didn't work anymore. Didn't actually do the substitution, which meant the ring had to be acting as an electrophile. And you needed the deactivating groups to withdraw that electron density from the ring so that the reaction could happen. Okay? We also couldn't follow the same general types of mechanisms that we had before. So what was the suggested mechanism? We make the bond, but we break the pi bond. Okay? What ends up happening if we do that?
You've got in the group a negative carbon.
You would have a negative carbon, which we might say is horribly bad, but stabilized through resonance with the electron withdrawing group. So that electron withdrawing group had to be located in a position such that it could stabilize that forming charge. Right? Once we formed it, it's unstable, and eventually the electrons come back in and now kick out the better leaving group of bromide. So what we end up doing is an electrophilic addition, because in step 1, what did we do? Break the pi bond, followed by an elimination, because we've now lost that bromine. So it's an aromatic reaction, but it's looking at a nucleophilic addition followed by an elimination. So you'll typically hear it referenced that way. Similar to what we might have expected back in chapter 21 and 22, 2021, with our acid derivatives. Okay? Very similar concept, except no polar pi bond, explicit polar pi bond. The NO2 is polar enough that it's causing the aromatic ring to act as a polar pi bond. Well, once somebody was able to do it once, they're like, well, what happens if you change the nucleophile? So they switched to sodium amide. Okay, different nucleophile, NH2. What is different about the NH2 nucleophile in comparison to the hydroxide nucleophile?
Stronger.
It's a stronger nucleophile, and if it's a stronger nucleophile, that might mean that the ring doesn't have to be deactivated. And sure enough, what happens is that if we jump up to a stronger nucleophile like sodium amide, we can still get that substitution reaction to happen, even in an activated ring. That's kind of cool. But at the same time, we got a different product. So 2 different things came out, which means this might be following a similar concept, but there has to be a divergence in the mechanism because we're getting a second product. So we have to be able to go through and explain why these different things are happening. Okay? So, the big deal, the ring must be electron poor for our nucleophile addition and elimination, right? Because we're trying to polarize so the nucleophile can attack. Okay? That's our primary objective. If we increase the strength of the nucleophile, it doesn't need to be as electron poor, but electron poor are better. Okay? There must be a good leaving group. That good leaving group being halogens have to be there. Why? Because you're trying to have an extremely reactive oxygen or nitrogen come into play. Okay? So we need a better leaving group than oxygen or nitrogen. Okay? And we have to have this position of ortho-para to the withdrawing group. Why? The nucleophilic addition forms a negative charge. That negative charge on a carbon must be stabilized. The resonance of your ortho-para substitution is what's allowing that. Okay? So some NAS examples. Both of these we could try and run. We'll find that one of them does not work. Which one does not work? The second one. Why not? If the electrons come in and attack, these electrons would swing around, then these could continue to swing. We never build a charge on the carbon where the withdrawing group is, which means that negative carbon is never stabilized. because it is never stabilized, that reaction doesn't happen. Kinda, sorta. This comes from drawing those resonance structures, which I would love to draw, but I would also like to finish this semester. Okay. So we could continue to go through and try and play around with reactions. So if we look at with the chlorine, sodium hydroxide, we don't get a reaction. Okay, with just heat. We take that same reagent, sodium hydroxide, now we do get a reaction. Why does it all of a sudden work now? No catalyst, it's sodium hydroxide. Heat! Heat was a bit vague. That heat is typically pretty low. You're looking 100 degrees maybe. 350 degrees Celsius. That's really screaming hot. That's why the reaction's happening. We're able to clear those activation barriers. Right? What happens if we now switch it up and drop in sodium amide? Well, now we get the reaction to run, and we're at what temperature?
Normal room temperature.
This says LIQ referencing liquid for what? Ammonia. What phase is ammonia?
Gas.
A gas. How do you get liquid?
It's cold.
It's cold. This reaction runs at, I think, minus 78 Celsius. So very, very, very cold, and yet this reaction works. Why? Stronger nucleophile. Okay? That's a pretty significant difference. Okay? So if we quantify it based off of temperatures, we're looking at a 400-degree difference in activity between our nucleophiles. That's actually kind of neat. I've never actually thought about it that way. 400-degree difference, oxygen versus nitrogen reactivity difference. That's kind of nuts. Okay? So, odd result for the NAS mechanism because we wouldn't really predict it to happen. Okay? But what we end up seeing is that we get something like this. And it looks to me like, oh, never mind, there it is, it's up top. When we run it, yes, we get that one product, but we also get a second. And that seems really weird. Nothing about our starting material has activity at that carbon, right? So why on earth would that happen? So what someone went through and did was said, okay, we know we're forming it, how could we form it? It's not following the NAS mechanism, because the NAS says that that shouldn't happen. There's no reactivity there. So instead they go through and they radio-labeled carbons to see what happened. Right? And in the process of radio-labeling those carbons, they noticed that they get a 50-50 mixture. This isn't just like a one-off side product. This is exactly half. Half produces one, half produces the other. Okay? How do I get both of those carbons to be equally reactive? Resonance doesn't work because with the chlorine there, they wouldn't be equally reactive. Is there a situation or a functional group that has equally reactive carbons? So I want this carbon to be and this carbon to be equally reactive. If I put on halogens, sure. Now both of them are equally reactive. Do I have two halogens? No. What's that? An ether. Did I start with an ether? No. The only thing I'm allowed to start with are these two carbons.
If you have to have an alkene.
If I have just a nonpolar pi bond, those carbons are equally reactive. But I can't have an alkene just to start with, and if it was an alkene, wouldn't the pi bond have disappeared in the course of the reaction? The chlorine also needs to somehow disappear. Could I form another nonpolar pi bond that wasn't an alkene? An alkyne? How do I go from an alkene to an alkyne? I would need to do an elimination, which means I would have to have a leaving group such as chlorine, and I would need a hydrogen at that position next door so that I could remove the electrons to kick that out. Yes? Look at the benzene.
CH
Is there a hydrogen there?
Yeah, there's a hydrogen everywhere except for chlorine.
Yeah, there is a hydrogen there. So if this base came in, removed that hydrogen, and did this, what would that form? I know it's a bit squished. We'll unsquish it in a little bit. I would now have an alkyne. Both of these carbons, red and green, would be equally reactive, or red and purple, would be equally reactive, right?
And it's outside of the ring too, just pointing out.
We'll deal with that in a second too. Both of those would be equally reactive, which means they could equally react with the rest of our reagents to place the sodium on there at either, the ammonium at either position. Yeah? But that would require that we formed a triple bond in the ring, right? Couldn't possibly do that, right? That doesn't make any sense. Turns out you can. Which is exactly why the ACS asked questions about it. Because the structure we end up with, the benzene, is so crazy and unbelievable that they're like, students won't believe it if it's true. So we'll throw a question on there and they'll never guess it. Okay? The benzene does exist. We need some particular chemistries to force it to happen. You have to have that stupidly strong base in the sodium amide. Okay? What's the hybridization on that star carbon? SP. Okay, again, no way in hell, but it does. Okay? We have evidence in the products that are formed. What is the exact shape of this? There's some arguments about that, but it's kind of a diradical. And as David was trying to suggest here, that extra lone pair is not part of the pi system of the ring because it's in an orthogonal orbital, okay, perpendicular to it. So the triple bond can't do resonance with everything else. And in fact, aromaticity dies altogether with the benzene too. Because to get those bond angles, you form a massive weird twist structure which destroys the pi system, okay, or destroys overlap of the pi system. Okay? So one of the approximations is that it comes in as a diradical instead of an alkyne. Okay? Not a big deal. Really the big deal is recognizing that it's an alkyne. What ends up happening once we have it? Okay? Well, that's a very unhappy structure that is dying to break open. Nitrogen as a strong nucleophile can come in and do a or not necessarily a backside attack, but attack the pi system and cause that to break open to form an anion. The anion can now pluck hydrogens off, okay, to get us to our final product. It is a crazy, bizarre reaction, crazy, bizarre mechanism, but it does work. Okay? How do we know it actually exists? Benzene. It's just how it's referenced. Because we got the triple bond and a benzene. The other reason why we know it exists, Diels-Alder reacted dienes with dienophiles. A benzene would be a really good dienophile. It's just a pi bond that wants to react. Aromatics won't react in a Diels-Alder. Benzenes will. And you can end up getting a Diels-Alder reaction coming out of it, which is really, really neat, personally. If we think back to standard addition reactions, HBr, Br2, all of those worked with alkenes. They don't work with aromatics. They do work with benzenes. Okay? So we can get these kind of bizarre looking reactions if we can generate that benzene intermediate. Okay? So there's all of our aromatic reactions. We've got them all written up there. You should memorize all of those. The next sequence we've got is to talk about polymers. For those people in lab, it will be a review. But really what I'm trying to zero in on polymers are the big kind of catchphrase points behind the polymers. We will finish that on Wednesday, and I hope that we will finish that in under 20 minutes, which would mean the majority of Wednesday can be spent answering your questions that you've got about material that we've covered this semester or first semester, for that matter. You do have the ACS study guide. I forgot to grab one from my office. Come back here. I do have some things that I picked from the ACS study guide, so we can talk about those. And then on Wednesday, you can tell me questions, and I'll just take pictures of them and do them live. Okay? Make sense? Yes?
Will you post last Wednesday's?
Did I not post it?